two more examples. I think we'll be pausing in the middle of this to talk about part B, and we'll be doing some different section. Okay, so let's write down the formulas that we will need here. So we're going to have that the second derivative gets sent to by the Laplace transform, s squared times the Laplace transform of the solution minus s times the value of the solution in time domain at 0 minus f dash to 0. We'll write our green picture as well. F dash to t by the Laplace transform gets sent to s times big F of s minus little f of 0, and finally little f of t, the notation we use, gets sent to big F of s. Now in this question, the role of f is being played by y. So everything, it won't be f's, it'll be y's. And let us draw our picture. So what we have here is a differential equation. Where do we draw it? We've got a differential equation here in the time domain, and what we want to find is y of t. That's essentially what we're looking for. So we translate it into the s domain using so we're going to turn the differential equation into what's called an algebraic equation, which is very easy to solve. We'll find the solution of that algebraic equation we call big Y of s, and then we'll send back with the inverse Laplace transform, and so we'll have a solution of the differential equation like that. So it's kind of, you could say it's a 3-step process or a 4-step process, depending on what you want to think. So first step anyway is take the Laplace transform of both sides. So the second derivative, so we're going to use this first formula here, except instead of f's, we've got y's. So it's going to be s squared times big Y of s. A lot of people see that as 1 over s. It's not, it's big Y of s. Maybe I can add a bit of funk to it there. I'll only do that once though. Minus s times, now it won't be little f of 0, it'll be little y of 0. Minus y dashed of 0. Now the next thing is something that catches people out. So people will write, they'll fix the 4, which is fine, and then they'll send the first derivative, and they'll get s times big Y of s minus y of 0. And as written, that's incorrect, because as written, there's BOMDAS, so you do multiplication before subtraction. So you'd multiply the 4 by the s y of s and then take away y of 0, but actually it shouldn't be like that. So it's very, very, very important that you put this bracket there like that, because it should be 4 times the Laplace transform of the derivative. And if you don't have that bracket, now you might not write the bracket and get it right, and if you get it right, I mean, obviously I don't care, but look, it's a mistake students make every year. Put the bracket there. Plus 4, little y of t is sent to big Y of s. Now, a lot of people might just not send the 0. I think you should, because there might come a time when there's not a 0 on the other side and you just leave it. No, you should send the 0. The 0 is a constant. It'll be sent to 0 over s, which sure enough is actually equal to 0. So now we apply the initial conditions, that y of 0 is 1 and y dash of 0 is 0. So I get s squared times big Y of s minus s times 1 minus y dashed of 0, which is 0, plus, now I can multiply this, I'll multiply it out now. See, if you have to multiply the y of 0 this inside in the bracket by 4 as well. If you don't, it's incorrect. It's a mistake that a lot of people make. So you get 4 by s by big Y of s, and then 4 by minus 1, which is minus 4, plus 4 times big Y of s equal to 0 divided by s is just 0. Now what we want to do now is solve that. I'm just going to write it down off screen. Now it's probably worth saying that first of all, this is minus s by 1 is just minus s. And we're going to be solving for big Y of s on the next page. So you want to get all the Y of s on one side. So get rid of this minus s by adding s to both sides, and get rid of this minus 4 by adding 4 to both sides. So I'm going to go from this line to the next line where I will have added the s and added the 4 to both sides. So what do I get? I get s squared times big Y of s. I'm adding the s to both sides, so that minus s is gone, plus 4s times big Y of s. The minus 4 is gone because I'm adding it to both sides, plus 4 times y of s equal to, so we said we're adding the s to both sides and we're adding the 4 to both sides. So this is where we are. What do we do here? Well, we take out the common factor of y of s. Common factor, common factor, common factor. So that's times s squared plus 4s plus 4 equal to s plus 4. And then we divide both sides by s squared plus 4s plus 4. So y of s is equal to s plus 4 divided by s squared plus 4s plus 4. So if we look in terms of our green picture, we have the big Y of s. Now we have to send this back. Now if we look in the tables, there is nothing like that there. Now what you do have is, say you have, let's write some of the things that are in the table. So 1 over s plus a, 1 over s squared, s over s squared plus omega squared, and omega over s squared plus omega squared. But none of them are, it's not quite right. Now what you'd be hoping is that maybe it looks something like that. So to get it like that, a sum of simpler terms, you need to do partial fractions. So the first thing is you have to factorize the thing on the bottom. So we'll do that. So s squared plus 4s plus 4. So we'll do the AC method. So that's 1 by 4 is 4. Look at the factors of 4, 1 and 4, 2 and 2. 3 doesn't go, 4 we already have. And can you make up plus 4? In other words, this, using a pair of these, adding them, yes, plus 2, plus 2. So I'm going to rewrite the plus 4s in the middle as plus 2s plus 2s plus 4. Okay, so what we have to do here is take out what's common out of the first two, which is s. What are you left with? S plus 2. And take something out of the second 2 that leaves s plus 2 again, which would be 2. And then you've got a common factor here of s plus 2, so take that out. And what are you left with? S plus 2. Now this is not rule 1 because they're not distinct, they're the same thing. Really it's more like s plus 2 squared. So you cannot use the cover-up method. Now it's a rule 2, and we're going to do the rule 2 in the notes, but we'll just do a shortcut here actually. Just if some of you can do this, you can go through it. So we've got s plus 4 over s plus 2 squared. Okay, so if we get s plus 2 on top, so the thing is, I think if the s on top isn't 1s, say if it's 3s, this gets a bit messy. You can still do it, but it's a bit messy. And then you can split this up as s plus 2 over s plus 2 squared plus 2 over s plus 2 squared. And then the first one you can divide above and below by s plus 2. And that is in fact the partial fraction expansion of it. Okay, so if there's rule 2s, there's sometimes a shortcut. So this is, we'll say it's tricky. Shortcut for rule 1. And I think it'll only work if you only have a rule 2, if you just have a single rule 2. Now I'm not going to do it that way. I'm going to do it more like the notes, particularly if you something with a rule 1 and a rule 2 where you'd have to do something a bit different. So what have we got? Rule 2. So we've got y of s, which is equal to s plus 4 divided by s plus 2 squared. Rule 2 says, so you got two factors, s plus 2 and s plus 2. You'd be tempted to do s plus 2 s plus 2, this is what you'd be tempted to do. But if you actually try and, that's a plus b over s plus 2, it can't actually equal the thing on the left. So you have to change the second term by squaring this. Okay. So so what are we going to do now? So we want this thing here to equal that thing there. So what we should do is write the thing on the right, the thing with the red A and the red B, as a single fraction and compare. And what we should use for a common denominator is the same common denominator as s plus 2 squared. Because a lot of us, I think, can write something that's strictly true, which would be a times s plus 2. So this is what maybe you're trained to do from school. And that is correct, but notice that the bottom of this is, terrible choice, is different. Now from there you can divide by above and below by s plus 2 to get it the same. But it's just going to be easier to say, okay, I want the thing with the red A and the thing with the red B, I want them both to be over s plus 2 squared. The second term is, so it's no problem. So all you have to do is just multiply the first term above and below by s plus 2, and that will do the job. Now you cannot square above and below. Like if you've got 2/3 and you square it, you have 4/9. That's changing it. So you can't do that, but you can multiply above and below by s plus 2, because that red thing, s plus 2 over s plus 2, is just equal to 1. Plus b over s plus 2 squared. So this is equal to, so how do you multiply fractions? I'm talking about the thing on the left here, the a over s plus 2 times the red thing, top, bottom, bottom. S plus 2 by s plus 2 is s plus 2 squared. Now you can go a bit faster on this as long as you're getting it right, but I'm just kind of methodically showing you mathematically how it actually does work, even if you skip a few steps. So you got common denominators, that's fine. So you got a times s plus 2 plus b all over s plus 2 squared. Now doing this question, what comes to mind is what I was saying last week about you can't know all the steps in advance. You have to just go step by step. Okay, like, so we don't have everything kind of, we just kind of say, oh, where are we now? So where are we now? Well, we can compare these two things, the s plus 4 over s plus 2 all squared and the thing with the a. And if the bottoms are now the same, so if I really want them to be equal, all I have to do is just make sure that the top of this is equal to the top of that. So compare the numerators. So I want s plus 4 is equal to a times s plus 2 plus b. Now if you want, you can compare coefficients. So if you compare coefficients, how many s's on the left? 1, and on the right you have a, so a must equal 1. And then compare constants. If you want to do that, that's fine. So the values that I think are clever are -2 and -1. Now usually, now -2 definitely works because it kills the a. So if I put s equal to -2, we'll do that first. So we'll get -2 plus 4 on the left hand side. Now the -2 is chosen because it kills s plus 2, and so that's 0 plus b, and we just find that b is equal to 2. Now the clever value, the reason I picked -1, I can't kill anything else. I suppose you could put in -4 to kill the left hand side. You can put in whatever you want. I mean, so I think I'm going to actually run with s equal to 0 because that's the next simplest. But s equal to -1 is clever because it'll make the multiple of a 1. And the other clever value might be s equal to -4, that you kill the thing on the left hand side. But I think I'm going to run with s equal to 0 just because it's a simple number. S equal to 1 makes sense as well. So on the left hand side, s plus 4 is 0 plus 4 equal to a times 0 plus 2 plus b is equal to 2. We just found that just above. So I have, if I take away the 2 from both sides, I get 2 is equal to 2a. And therefore there's loads of space here. Divide both sides by 2, a is equal to 1. So a is 1 and b is 2. So the y of s, this thing here, is equal to this thing with the a's and b's with a equal to 1 and b equal to 2. So I get to here. Okay, now you'll notice that's exactly the same. Whoa. As well, the shortcut that we did. I'm just going to pause while the dog is barking. So now our job is to send this back. What about the other term? So I don't know why I got a line break there. Okay, so we know the first term is easy, okay, because we have 1 over s plus a in the tables. The second term is a little bit... Now the 2 isn't an issue, right? So the 2, we can just take that out. It's 2 by 1 over s plus 2 squared. So don't worry about the 2 on top. So if we look in the tables, you can probably compare it with... There's some things that you could compare it with. You could compare it with omega over s squared plus omega squared. But it's just not of that form. Like it isn't s squared plus something squared. That's not working. And you have to look in the tables and have a good think. And obviously the best way to get good at this is to do lots of questions and get used to it. But this is actually like a 1 over s squared, but shifted. So instead of s, you have s plus, now it's s plus 2, but in terms of the formula it's s plus a. So it's a shifted 1 over s squared, and we're just forgetting, we're not worried about the 2 at the start. Okay, so see what I write up here. So what you need is what 1 over s squared is sent to t to the 1. Okay, so let's write down some stuff here. So what we definitely have is that 1 over s squared, using this formula, this 3.17, gets sent to t. Okay, so that's definitely there. But the 1 over s plus 2 squared, well, how does it send back? If it's shifted, well, we would have spoken about this before. If instead of s, you've got s plus something, then you've got a shifted term. And what you do is you bring it back as normal, except you multiply by the exponential shift. Okay, so what we're going to have is little y of t. So what are we sending back? So the 1 over s plus 2 is no problem. That's just going to go back to, so that goes back to e to the minus at. So the first term is going to go back to e to the minus 2t. That's no problem. For the second one, we're going to fix that 2. So what am I talking about fixing the 2? So the 2 over s plus 2 squared, I can fix the constant 2. And then what happens with 1 over s plus 2 squared? Well, it's written in the line above. 1 over s plus 2 squared is a shifted 1 over s squared. And what the first shift theorem says, and we'll write the first shift theorem over here, it says that if you've got something that's shifted, so this is basically the start of it, and the shifting says if instead of s you've got s plus a, then when you bring it back you multiply it by what we call an exponential shift. So the 1 over s plus 2 squared comes back, it's a shifted 1 over s squared comes back as normal as a t, but because instead of 1 over s squared we've 1 over s plus 2 squared, we multiply by this exponential shift. Okay. Now there's the second question there about it models a door closer. Is it well designed? We're going to just do a little section on door closers and stuff like that. So I'm going to pause the video and find the right page. So here's the section on the door closer, page 138. Now we might have actually covered some of this already, but there's no harm hearing it again. So I think we did the first bit. I'm not sure if we did or not, but basically if you have a door closer with just a spring, it's going to slam. So you have to add in a damper. And you'll end up with this equation here, basically. And it comes from Newton's second law. Okay, now what we're going to do here is just kind of talk about the different behaviors that you can get. So what you can get is, we might just say that this is the damping. Well, this is minus the damping force. Because the so let me just say that this is acceleration, because it's the second derivative of displacement. So you do mass times acceleration is equal to sum of the forces. And on the right hand side, you'd have the damping force plus the spring force. And they both have a negative in them. So when you add those things to both sides, that's why they become plus over here as such. So basically it's a kind of a trade-off between the damping and the spring. Now usually you think of the spring as fixed and you adjust the damping. So you'll talk about the door closer being underdamped, overdamped, or critically damped. Sorry, the dog is playing with paper. I'll try and speak clearly, so you might hear a little ruffle. So yeah, so you've got a fixed spring and you're thinking about the damping. So the damping, basically the job of the damper is as the door is closing to slow it down so it doesn't slam. Now if the damping is too strong, what's going to happen is the door is going to take too long to close, basically. If the door is underdamped, the door will slam or swing if there's no door frame. And in between the overdamping and the underdamping is critical damping, where the door closes as fast as possible without slamming. Okay, so this is the full analysis, which we won't go through. So this is, yeah, this is mega, right? So there's so this is the situation you get to here. So what you should be doing here is, this isn't in the table, so you try and factorize this. So I think the first situation is when that. So the first situation is when you can factorize the bottom. Okay, so if you can factorize the bottom, you're going to have this should be minus beta. Yeah. Then you'll end up with having two roots, and you get a factorization here, basically like this. So if you can factorize this, and if you can factorize it, then what are you talking about? You're talking about rule ones. So if you get to here, you have rule one, and so you can end up with this. Now what happens here is you send them back, and in fact I can change these minuses to pluses, and I could do that the whole way. Well, let me see, we'll do that the whole way, yeah. No, I can't really do that. So the gammas are actually negative. Sorry about this. So the gamma plus and gamma minus are both negative. Okay, so what that means is you got two negative exponentials here. Okay, and whenever you see this, this is going to be overdamped. And this is something we would have covered in chapter 2. What happens is one of them goes to 0 quickly. So if so if, say for example, if you had x of t equal to e to the minus 2t plus e to the minus 4t. So the second term goes to 0 really quickly, and then the other one takes much longer. I'm going to pause and I'm going to go back here as well. So way back on page 66, we actually looked at this. So the red thing here is the sum of e to the minus alpha t plus e to the minus beta t. Now one of these, if beta or alpha is bigger, they'll go to 0 faster. So say alpha, is bigger than beta, then do you see the blue one? That would be the e to the minus alpha t. So that goes to 0 quite quickly, and the other term goes to 0 slowly. And so their sum, which is the red line, has kind of got a 2-track speed. You've got a kind of a period where it's basically it's going to 0 quickly, and then it really slows down. So this is the kind of the fast and slow. Fast and slow. And have you ever seen a door with a door closer where it closes really quickly and then it takes all day to actually close off? So it starts, it nearly closes and then it takes ages to close at the very end. So that is symptomatic of overdamping. And when you have two negative exponentials, it's overdamped. Okay, so that's what's going on here. The second possibility, so this is large damping, this should really say overdamping. So you see the period, this is the fast bit, and then the slow bit. And the door closer fails to close quickly. Well, I would say it actually does close quickly, but fast at the start and then slow. So the second possibility is small damping or underdamping. So what happens here is that the door is basically being pulled by the spring, but the damping isn't enough to stop the door before it slams. And so in this situation, what you have is you've got no real roots, and so there's no real factors, and so you have to complete the square. And when you complete the square, what you end up with, you end up with cos's and sines. So you end up with this thing. So you end up with two terms, one which does go to zero and a wave. So basically you've got a wave going to zero, something like this. And this is underdamping. So if there's a door frame, it will slam. So this is the slam. And if there's no door frame, the door will kind of come back and forth. It will eventually close in the limit, but not very well. Now there is somewhere in between two real roots and no real roots, and that is one real root repeated, and that's the critical damping. So this is like the question that we're actually stuck in the middle of. And so what happens here is that now there's an extra t term, but we won't worry too much about that, but give or take, these are the same speed. And so the door pretty much closes at one speed. It doesn't, if it closes at two speeds, it's overdamped. And if the other possibility is if it slams, so this doesn't slam. So this is what's called critical damping. So you see it here, it's kind of pretty much the one pace. If you push this a little bit further, if you tried to close it a bit faster, you'd get a slam. So critical is about as good as you can do. So the three types of behavior when you look at a damped harmonic oscillator or a door closer is underdamping, overdamping, and critical damping. So the question is basically I think the best thing for you to manage is just look at the solution, rather than doing what's suggested here. Yeah, so there's all these different options. I think the best way is just see which solution, see which behavior the solution corresponds to. So I think we're going back to something like 135 now. Back further, back further, back further. Sorry, this is a great video, isn't it? So here you can see that you've got two exponentials of the same size, so it's critically damped. Because the question is, what's the question? Suppose the differential models a door closer. Is it well designed? You say yes, because it's critically damped. This is a well-designed critically damped door closer. Now, if you plot it there, it doesn't look great, but if you actually try and so it looks like it's overdamped, but if you make the damping any bit weaker, so if I go back to so this is the damping term. If I change that to something, wrong symbol, lambda less than 4, then the roots are going to be complex and you're going to get sines and cosines. So it's as good as you can do. Okay, so we're going to have one more. I think the next one is going to be underdamped.